All right, so let me show you, before we get into the hard stuff, let me just demonstrate the concept that we're going to be discussing today, just in case you haven't got it yet. We've been talking, I've been hinting for the last couple weeks about this concept of precedence and that we were going to figure out how to do it. Let me just try to drive home what's going on here. You all did golden ears last semester, and we were playing around with delays, right? And you noticed, hopefully, that by manipulating the delay between the two channels, you either would hear an echo, right? If the delay got high enough, you would start hearing the sound twice. But if the delay was within a certain range, it would just kind of sound like it was coming from one side or the other side. Did you notice that? Yeah. What was that range where it sounded like it was coming from one side?
Entirely, or
yeah,
like 1 milliseconds. Like it would be like 1 to 10.
Yeah.
Because like from like 0 to 1, it's shifting over. So but starting at 1.
Starting at 1, yeah, you'll start basically. You'll just think it's coming from whichever side got to you first, basically. And then how far could you push that before you started being able to hear double?
Like 25, 30.
Yeah. It kind of depends on the source material, right? Like, I think when we did the percussion, that we got to that point sooner, right, or that echo point sooner. But when we were in music, we could maybe push it a little bit farther. Let me just demonstrate this again. What I'd like you to do is, you may have to get up out of your seat because you do need to get your head kind of in between the two monitors here. And I just want to demonstrate the thing. I've got this max patcher that will do level panning or delay panning, and I just want you to hear the difference. So get up out of your seat if you have to, and get your head somewhere in between those two monitors. And I just want you to hear what this sounds like. If you're not like perfectly in the middle, you'll still hear it. It just won't be quite the same thing.
On an open sea, I'd stand at the railing.
So sounds like it's coming from the left, right? Now it sounds like it's coming from the right. And if I put it, in the middle, it sounds like it's equally coming out of both, and maybe it sounds like the voice is somewhere in between the two. Okay? Yeah, now I'm just doing level, right? So you can look at the meters, and the left is the only one that has a meter on it. It means there's no sound coming out of the right, okay? And as I move it over, there's a little bit coming out of the right, but more coming out of the left. Okay, so now I'm going to switch, and now I'm going to pan with time.
I'd rather be sailing, yes I would, on an open sea. I'd stand at the railing.
But what's interesting about that is there's the same amount of sound coming out of both loudspeakers.
Feeling wild and free.
And I can move it over to the right.
The sun is on my neck.
So now it should sound like it's coming more from over here.
In my face.
Now,
the water.
What's interesting about this?
Blue, and I'd rather be sailing.
Okay,
yes,
I just unplugged the left.
Wanna go sail,
okay,
and then come home to you.
So what you notice is, when I unplug it, it just gets quieter, right? It still obviously sounds like it's coming from the right, but you realize that left one was on, but what it was doing is giving you the impression that the right channel was louder than it was. Okay, this is called the Haas effect, named after a guy named Haas, who did this research and wrote this paper. And he was specifically researching stereo imaging and the role that time delay and arrival times played in stereo imaging, because for the most part, stereo imaging is just accomplished by level, right? You just put things louder in one channel than the other, and it gives you the impression that it's moved in that stereo field. But what he was researching is what role time played in that perception as well, and he realized that time does play a perception, or can play a role in that perception. And what he basically observed was that you could hear the same sound twice, and if there was a certain amount of time between the two sounds, you would just think that both sounds came from whichever angle arrived first, right? So whichever sound arrived first, and wherever that came from, you would think both sounds came from there, okay? Until you got to a certain point where that delay was so much that you started hearing double, okay? And as you've noticed, that delay varies, right, from material to material, and program material. So that was the thing that sort of Hasplit was playing around with. And what we've done since then is we have, a lot of people have done a lot of research and experimentation on that basic concept, and we now use it for a lot of different things. But a lot of what Haas observed and discovered is basically the same thing that's going on inside of rooms. When we have early reflections, when we have helpful early reflections, the kinds of reflections that make someone say that this room has good acoustics, what they mean usually is that there are reflections, sound is reflecting off walls in this room in such a way that that reflection gets to the listener within that special window of time. And therefore, the thing on stage making the sound just sounds louder to you. You don't perceive that the sound is coming from the wall, you perceive that all the sound is coming from the person. And that person just sounds louder because of that reflection and the timing of that reflection. And that is essentially the same effect as the Haas effect. It's the same basic concept. So before there were such things as sound designers, there were just architects, and architects built nice rooms that had good early reflections, and sometimes had bad early reflections, and those were considered to be not very good acoustic spaces. But spaces that were considered to have good acoustics tended to have helpful early reflections that would leverage this, we call it a blind spot in our hearing system. And it's a blind spot we've developed just out of necessity, because if we couldn't ignore those different time arrivals, then everything we hear would just be chaos. We could never understand anything we heard, because we'd just be hearing 30,000 different versions of it all at the same time. And if we perceive those as distinct events, then we couldn't communicate with each other. So we have, over millions of years, we have just figured that out, right? Our ear-brain systems have adapted to that phenomenon, which means you can kind of count on everybody having this similar blind spot, okay? And therefore we can exploit it. And while we don't always build really great rooms anymore that have really helpful early reflections, now we have sound designers like us that can put in sound systems that pretend to be good rooms, okay? So one way of thinking about a sound system when you're designing a sound reinforcement system is basically you're going to put a loudspeaker everywhere there should be a wall. Everywhere that there ought to be a wall that would help make an early reflection, you just can put a loudspeaker there instead, and that loudspeaker can pretend to be a wall that's creating a helpful early reflection. And if you do that just right, then you can get this sense that whatever is on stage making that sound is louder than it normally would be, because the sound coming from the loudspeakers is hitting the audience a little bit later than what we call the direct sound. And if that happens, and it happens within this window that we've observed, that 1 to 25, sometimes you can push it as hard as 30 milliseconds or so, then you'll lump it all together. There's another little rule of thumb, which is that even if you have that window correct, with that time window correct, if there's more than a 10 dB difference between the two sounds, then level starts taking over. So if that second sound that is delayed it can be as much as 10 dB louder than the first sound, and you'll still image it to that first sound, that first arrival. But if that second thing gets 10 dB or much more past 10 dB louder than the original, then you'll start that image will start shifting towards the second sound. The other interesting thing that we've discovered is that this effect can be daisy-chained. So where you could hear two sounds, and one of them comes a little bit later, between 1 and 30 milliseconds later, and you'll image both sounds to the direction of the first thing. If you have a third sound, that sound could be as much as 50 milliseconds after the first one. And even though that would normally cause you to hear an echo, if you still had that second one that was arriving within that precedence window, then that third sound is arriving within the precedence window of the second sound. So in other words, the third sound images to the second one, and because the second one images to the first one, then the third one also images to the first one, right? So you're hearing it now 3 times, but you still think it's all coming from the first arrival. And so because you only can get at best a 10 dB boost off of that second sound, sometimes 10 dB isn't quite enough for us. It's not quite enough gain for us to feel like we should get paid for what we're doing. So we can hit the audience with a second, or a third sound, basically, that is within the precedence window of the second one, and we can theoretically get as much as a 20 dB boost between the direct sound and the reinforced sound, and that's a good difference. A 20 dB difference between you not showing up to work and you showing up to work is good. That's a difference that somebody would pay you for. Okay, so keep that in mind. So let's talk through now how you would figure this out. Stick with me, because this is tricky. Anybody? Well, first of all, when I did the demo just now, what made it work is I was able to put you all in basically the same place horizontally, right? And that's what made it work. We don't get to do that with our theater audiences, right? They're going to sit all over the place. So every place they sit will change the distance they have between the actors and the different loudspeakers. And every time their relative distance changes, then the time at which all those different sounds arrives at them will also change. And we're trying to make those times arrive at a very specific window. So if the audience is all sitting in different places, we have to figure out a way to make it work for all the different places that they could possibly sit. If we only had one listener and they were sitting in one seat, this would be a piece of cake. But because our audience sits in, could be 1,000 seats or more, we have to figure it out for all those different possible places they could sit. And that's tricky. Okay, so let's start there. First of all, let's figure out where our talker is going to be. So this is the Stevens Center, and I think that, let's say this is something like commencement, where someone's just standing at a podium and talking. Okay, keep this simple for now. They're probably going to stand somewhere around here. That's about as far down as they'll be. So let's just say we'll put the podium there. Okay. It's probably not realistic to expect that we could figure this out for every single row and every single seat, right? But if we could make it work for the front row, and we could make it work for the back row, then it's a safe bet that it's going to be working for everybody in between. Okay, we can use that as a working hypothesis, and then we'll discover in real life whether that's true. And then usually that's true. So I'm going to put a little listener on the front row, and I'm going to put a little listener on the back row, and I'm going to do the same thing for the balcony. So front row balcony is going to get a person, and back row balcony is going to get a person. And just because this is going to be a lot of data I'm going to have to keep track of, I'm going to just use Excel to help remember things for me. But you should be writing them down too, because sometimes I might forget. Okay, so I'll do orchestra front, orchestra back, balcony front, balcony back, and I'm going to need a column here. Okay, so the first thing I want to know is the talker distance. In other words, how far away is the talker from each of those places? It's the first thing I want to know. Let's see if we can figure that out. So the talker is 19.3 feet away from the front row. And the talker is 78 feet away from the back row. And the talker is 62.5 feet away from the front row balcony. And the talker is 102 feet away from the back row balcony. Okay? That's how far they are. How long will it take for sound to get to those places? Yeah, so we need to convert this to milliseconds. Anybody remember that math? Yeah, remember it's 1.13 feet per millisecond, right? So if I take that distance and divide it by 1.13, then I'll get time. So I'm just going to use Excel to do some of that math for me. So if it's 19 feet away from the front row, the sound will arrive 17 milliseconds later. It'll take 17 milliseconds to travel 19 feet. And I'll just copy that over there, and that means it's 69 milliseconds to the orchestra back row, 55 milliseconds to the balcony front row, and 90 milliseconds to the balcony back row. Okay? 90. Oh, second to last, 55. I think I can zoom in here. Would that help? That would help. There you go. Okay, so talker distance, talker time. So I know how far away they are, and I know how long it's going to take the sound to get to those places from the talker. Let me go ahead and save this just in case something happens. All right, so now we need to add our sound system. Okay, so we've got a center cluster that lives somewhere around here. Yes? In space. So I'm going to call this my center cluster distance. Let's find out how far away the center cluster is to each of these places. The center cluster is 40 feet away from the front row. And the center cluster is 77.5 feet away from the back row orchestra. And it is 53 feet away from the front row balcony. And it is 88.5 feet away from the back row balcony. So now I'd like to know how long it will take for the sound from the center cluster to get to each of those places. Because this is about time, not distance, ultimately. So I do the same math. We'll do that distance divided by 1.13. So if it's 40 feet away, it's 35 and some change milliseconds away. To the back row, it's 68. Front row balcony, 49, almost 47 milliseconds. Back of the balcony, 78 milliseconds. That's the amount of time it'll take for the center cluster to get there. Okay. So now I just need to figure out what the difference in those two times are, so I know when those things get there. So what I'm going to do is I'm going to take the center cluster time minus the talker. And what I want is I want the talker to arrive first. Yes? So if that's happening, and I do center cluster minus talker, I should get a positive number that represents the amount of time that the talker arrived first, right?
For the areas the seats for that time.
Yeah.
There's some places.
We'll find. I mean, yeah. Oh, if I get a negative number, then that means the center cluster arrived first, right? So let's just see how that works. So I'll do center cluster minus talker. 18 milliseconds at the front row. And that makes some sense, right? If you just look at it, the talker is closer to the front row than the center cluster is. So I would expect the talker to arrive first. The center cluster arrives 18 milliseconds after the talker. But if I then take this math and copy it over, I have negative numbers everywhere else. Okay? So at the orchestra back row, they're arriving at almost the exact same time. The center cluster is arriving half a millisecond before the talker. But then we get up to the balcony, and the center cluster is arriving first. The center cluster arrives 8 milliseconds before the talker and at the front row balcony, and almost 12 milliseconds before the talker at the back row balcony. So that's not good, right? I want the center cluster to arrive afterwards, because I would like the audience to think all this sound is coming from the talker. So what would I have to do in order to push this into a window that would work? I would have to delay, if I could have some ability to delay the sound coming out of the center cluster, then I could slow it down a little bit and turn those negative numbers into positive numbers. So what's the worst case scenario here? It's that 11.9. And remember, we said that it'll start imaging at 1 millisecond of difference. However, we usually like to be at least 5 milliseconds, because between 1 and 5 milliseconds, that's tight enough that the comb filtering sometimes becomes problematic. But if you can get it into a 5 millisecond difference, then usually the comb filtering gets bad enough that you'll ignore it. So I would like to turn that negative 12 into a positive 5, which means how much delay would I need to put on the center cluster to make that happen? You say 17 milliseconds. All right, so what I'm going to do is I'm going to modify my formula here. I say, don't get ahead of me. Oops. Oh wait, did I do that the wrong way? Yeah, I did that the wrong way. So I need to add that in. There we go. Now I can copy it over. All right, there we go. So that puts me into precedence for every seat except now the front row. The front row is now, there's now a 35 millisecond difference between the center cluster and the front row. That's probably not going to work. In most cases, we'll start to hear an echo there. So some things I could do Can you think of something I could do to this? Don't get ahead of me. I'm not doing that yet. Just something I could do to the center cluster. I could move it, right? I could move it. If I could get it closer to the front row, for example, then I could get that to change. So yeah, let's say, all right, well, okay, maybe that location is not awesome. Maybe I'll instead move it down here and hang it on the truss underneath. Okay. In fact, I'll drop it a little bit further down. I'll have to fight with the pretty committee over that, but I'll see if I can cheat it down a little bit further. Okay, so let's get some new distances here. So now distance to the front row is 30 feet. And distance from center cluster to back row orchestra is 76.5. And now we're going to front row balcony, that's 54.5. And now we can go to the back row balcony. And we're at 92.3, let's say. Okay, that's better now. See that? Now I'm within 5 to 30 milliseconds, so my difference now is 8 milliseconds to 26 milliseconds. That's within precedence range for every seat. Piece of cake, right? All I got to do now is add 17 milliseconds of delay to that center cluster, and I'm in business. However, that's if we're doing commencement. What if we're doing a musical in here? What variable is going to change? Yeah, let's pretend that that's not a problem for now. Something about this geometry is going to change if I'm going to do musical theater. Yes, the people are going to be moving. Have you ever seen a musical where the singers stood still?
Briefly.
Yep. So, yeah, they're gonna move around, and as soon as they move around, then the amount of time it takes for their sound to get to the audience will change every time they move, right? And therefore, the difference between their sound and the loudspeaker will change. And I do not have a whole lot of room to tolerate that kind of difference in here. Let's see what that would look like. So this is probably as far downstage as they're ever going to go, right? Because presumably we'll have the pit open, and they're not going to stand right on the edge of the stage because they're going to be afraid to fall off. So they're not going to go any further down than that. But let's see, so yeah, there'll be some scenery up here. So maybe reasonably they might go 20 feet upstage. I would say that's probably where most of the action will take place, because there will be scenery back here. They'll do drops and staircases and stuff like that. So they'll do most of the singing in that area. So I need to add a variable here now. So I'm going to say downstage talker distance. Now I need to insert an upstage talker. And I need a distance, and I need downstage talker time, and this will be upstage talker time. Let's see what happens now if they start moving around. How far away is the upstage talker? So same strategy here is if I can make it work for the downstage talking location and the upstage talking location, then presumably it ought to work for all the places they could stand in between those two places, right? That's the working theory, and that usually is true. So the upstage talker is 39 feet away from the front row. And the upstage talker is, let's see, 98 feet away from the back row. And the upstage talker is 81. What's that? That's probably 0.25, 81.25 feet away from the front row balcony. And $120.5 feet away from the back row balcony. Let's convert that to time. And I'm going to modify this guy to say center cluster minus upstage. And now I'm going to do a center cluster minus, oh, that's upstage. This one's downstage. So the original was the downstage position. So same kind of math, but instead, now what I'm going to do, so just remember I did the center cluster minus the talker plus the delay that I added to the center cluster, right? So I'm going to do, this will equal the center cluster time minus the upstage talker time plus that delay. And let me go ahead and lock that cell in place so I can copy this over. You guys ever see me do something in Excel that doesn't make sense to you? Just ask me and I'll explain what I did. Okay, I'm in trouble again. You see that? What could I do to get myself out of trouble? I would need to add, in this case, the center cluster is now coming 8 milliseconds before the upstage talker. So I need to add more delay to my center cluster. Well, if I take it up to, I would need to add another 12 or 13 milliseconds to this thing, right? So I'm really looking at now 30 milliseconds of delay in the center cluster. But oh, that puts me into a 40 millisecond difference between the downstage talker and the center cluster, which I can't do. Can't do that. So there is no single number that I can put in here that will make this work. Okay. That's still, I take it down to 25, I'm still at 34 milliseconds. So I could take it down to 20. And now I'm into that 30 millisecond window with the front row for the downstage talker, but I'm now at a negative 5 milliseconds at the back row balcony for the upstage. So it doesn't work. We can't do the show. Okay. Well, let's go back now and just remember what changed, because we made it work and then now it's not working. What changed between when it worked and when it didn't work? Huh? Yeah, but why did that change?
Because he decided to check it. Yeah, so
because the talker started moving, right? So the talker started moving around, and that's what blew it. Okay? So our options are, we do a musical with no choreography, and they just stand still. Which, that's obviously not going to work. But essentially, if we could figure out a way to get the actors to not move, then we'd be okay. Well, we can't do that. They're going to move. But can we pretend like they're not moving? Yeah, we can, actually. There's a little trick we can do to pretend like they're not moving. And it's called front fill loudspeakers. Okay, so this is a bit of a misnomer because we call them front fills, but actually that's not why we use them. We don't really use them to fill in the front. Usually, hopefully, you've designed a good enough center cluster that hits the front row just fine. Thank you very much. So you don't need the front fills to fill in the front if you've done your job right. But what you do need is actors that don't move. And that's what a front fill can do, is a front fill can pretend to be an actor that doesn't move around. Because the problem of the reason why the actor moving breaks it is because that relationship between the actor or the talker and the loudspeaker changes too much. But we know we can make it work if they don't move. So if I can put a little loudspeaker here on the edge of the stage, and I know that I can set up the delays such that I can make that center cluster image to that single loudspeaker for every seat in the theater. Because that's what I did first. So I know that that will work. And then if I can just figure out how to get that front fill to image to the talker no matter where they are, then there's the daisy chain, right? And that should be possible because now the front fill is on the same plane as the talker. And therefore, the difference in time will not be as dramatic. So it ought to stay consistent for all the seats. Let's see if that's true. It is true, but let's prove it. So I'm going to put a loudspeaker right there. And we'll call that my front fill. The other interesting thing about front fills is if you start thinking about them in terms of talkers that don't move, you'll realize that they don't have to be very loud. They only have to be as loud as the talker is. Because that's all they're trying to be, is a talker that doesn't move. And therefore they can be small, and they don't have to be loud. You don't have to get your gain out of those. As long as they are putting out the same volume as the talker is naturally putting out, then they will do what you need them to do. Okay? So they don't need to be big. They don't need to have a lot of gain. Because now, from a gain for feedback point of view, we're now putting a loudspeaker right next to where the microphones are. So if we're trying to get all our gain out of that front fill, we're not going to get very far. So just keep that in mind. You don't need to get a whole lot of gain out of there. All right, so I'm now going to insert a new thing. This will be my front fill distance and my front fill time. So my newfangled front fill loudspeakers are going to be 16.5 feet away from the front row. And they will be 76.5 feet away from the back row. And will be 62.5 feet away from the front row balcony. And it will be 102 feet away from the back row balcony. Let's convert that to time. All right, so there's my times for the front fill. So here's what I'm going to do now. I'm going to modify these two things. I'm going to get the center cluster out of the equation for a moment. This is now going to be front fill minus the downstage talker and front fill minus the upstage talker. So in this case, instead of
front fill to the talker.
Yep. So in this case, I want that one. And that one. And I'm going to make a new center cluster delay, and this one now becomes my front fill delay. Set that back to 0. All right, so interestingly enough, if we look at this here, the front fill and the talker arrive basically at the same time to the balcony seats. And you could kind of imagine why that would be the case. From the point of view of that listener, those are essentially the same distance. Okay, so you can imagine why that would be the case. But good news is we've got pretty much all negative numbers here if you count the zeros. So how much delay would I need to add to make all these negative numbers be at least 5? Well, the worst negative number is that 19.9, so 20. So I would need to add 25 milliseconds. So if I add 25 milliseconds to my front fill, then look what happens. Everything sits now in between that 5 to 30 millisecond window that I need it to be. Yay! Easily within the precedence window now. And that works. So now I can ignore the talker. From my math, I can eliminate that now because they can move anywhere they want within that range, and they're going to image to those front fills. So now all I got to do is image my center cluster to my front fills, and I'm done. And I know that that's possible because I did it before. So now I'm going to say center cluster minus the front fill. Right? So, but I also have to include the delay into there. So that gets a little tricky. So we'll do, this is going to equal center cluster time and minus the front fill time minus the front fill delay, right? But also, it would be minus or plus the center cluster delay.
What was the question?
Trying to decide if I need to subtract or add the center cluster delay. I think I need to add it. Yeah. Yeah, because the center cluster delay becomes the bigger number. So center cluster delay plus, or center cluster plus the center cluster delay minus the front fill time and the front fill delay. That should do it. And let me just lock those in. And if I just put the dollar signs in front of these, then I can copy those cells and it won't change those reference cells. Okay, look at that. So how much delay do I need to add now to my center cluster to make this work? Yep. Take it to 39 maybe. Yeah, that puts me within range here. So these are the numbers I'm primarily interested in now. If I those need to all be positive numbers between 5 and 30 milliseconds, are they? Yes, they are all positive numbers between 5 and 30 milliseconds. Therefore, this will work. So what this means is, no matter where, if I'm sitting at the front row, I will hear the talker first. And if the talker is downstage, then 22.5 milliseconds later, I will hear the front fill. And that's a window of time where I will ignore those two arrivals and just lump them together as one thing. And then 25 milliseconds after that, or 26 milliseconds after that, I will then hear the center cluster. And that's within enough of a window that I will ignore that as well. But I will hear both of those things as extra sound, and therefore I will perceive the entire thing to be louder. But I will think it all comes from whatever hit me first, which happened to be the talker. Same thing for all of these seats. When you get to the back row and things tighten up a little bit, the back row balcony, I get, if they're standing downstage, I hear the center cluster 25 milliseconds, or the front fill 25 milliseconds after the talker, but then only 5 milliseconds after the front fill, I hear the center cluster, but that's still within the window. Now, just a little rule of thumb to watch out for is that, remember I said you can get as much of a 10 dB difference? So that second sound can be up as much as 10 dB louder. and then the first sound, and you'll still image it. Well, that 10 dB is a bit of a moving target. I have found that you really only get that full 10 dB. There's a sweet spot of time for that, and it's about 10 milliseconds. So if you're at about a 10 millisecond difference in time between the two sounds, that's when you can really push it all the way to the 10 dB. But if you're if you're much less than 10 milliseconds or much more than 10 milliseconds, you never quite get the full 10 dB. So that's something to think about as well. How could you push all of these numbers into that 10 millisecond range in order to get you the most gain possible? There's not really a way to do it without vastly changing something. I'll tell you the way that I've done it in this particular space before, because this geometry is just really weird because of the rake of this balcony. I usually will hang 2 center cluster loudspeakers, one pointed for the balcony, one pointed for the orchestra. And in fact, if we use the one in the eyebrow, there's 3 in there, which gets you the same thing. And you can delay them differently. So I can delay the one shooting at the balcony differently from the one shooting at the orchestra. And then at that point, I can get much closer to that 10 millisecond window for all the seats if I can separate those things out into 2 separate sounds. I'm not going to do that now because I think I may have fried your brain enough already. But those are the kinds of things you have to think about when you're trying to make this work. Is, well, okay, maybe I could break this up into more than one. This idea, by the way, remember when I've said this before, the best kind of sound system has 1 loudspeaker. Why did I say that? What?
All the rags is one loudspeaker.
Yeah, you don't have to worry about comb filtering, right? It's the most coherent. That's why it's the best. This idea just blows that theory out of the water, though. So going with this kind of a system, you are fighting against that idea. You are trying to add as many loudspeakers as you possibly can. And you're going to force them to interact destructively. Right? So you're giving up something to get that. You're giving up that coherence. This is not going to sound very coherent. There will be, if you measure these, that listening location and look at phase response, it's going to be a disaster. Okay? And you look at, the actual frequency response, if you could get it down to like 48th octave resolution, it would be just a mess, a complete mess because of how bad the comb filtering is. Okay? But what you're banking on is that most people have developed the skill to ignore that comb filtering when it gets that bad. That's what you're hoping, is that the comb filtering was happening within that critical bandwidth resolution of our hearing. So you'll ignore it. So you do lose that. And there are people who just are unwilling to give that up, right? So there are plenty of sound designers out there that will tell you this is really a bad idea. And they're not wrong if coherence is your #1 priority. So if what you want is to minimize comb filtering at all costs, then you can't do this. You can't do precedence. You can't have both. You can't have both coherence and precedence at the same time. You can have one or the other. So you have to decide what's more important to you. If you give up precedence, then what that basically means is that you are going to have, it's going to sound clearer, potentially, and cleaner, but it's not necessarily going to sound like it's coming from the talker. Right? No one's going to believe that all that sound is coming from that person. You'll just have to accept that sound is coming from loudspeakers that are up in the air. And if that's okay, then that's okay. Right? If that fits the aesthetic of the show, there are some shows that makes a whole lot of sense for. Right? A lot of modern musicals are written in a way that precedence doesn't really make sense for it, because it's it's a lot of sort of like modern pop rock sounding music, and maybe that sound of it naturally coming from that person is not really important to the artistic style of the show. And that's okay. It's okay to give that up. You just have to make sure you understand what you're giving up to do it. Yeah.
Will you show your Excel spreadsheet again?
Yes. So here's what I would like you guys to do over the weekend. I'm sure you all have plenty of time to do this. This is, you can get this off of Walrus. This is the CAD file from Company. What I would like you to do, which of you worked on Company? A few of you did. Okay, so you're familiar with this. What I want you to do is figure out the delays you would need to put on for Company. Now, there's a lot of loudspeakers in here. The only ones you need to worry about are the Q7 and the E3 front fill, because those are the only ones that had anything to do with vocal reinforcement. The rest of them were all reverb or monitoring or playback or whatever. So you know where they hung the Q7, and you know where they hung where they put the front fills. So what you need to do is figure out where the acting is going to happen, because this is the other problem here. Is obviously it's very difficult to make it work for every single spot on the stage, right? They can't. There's a reason I put the upstage talker only 20 feet upstage of the downstage is because much more than that, and you are hitting. Remember, it's about a foot per millisecond. And if there's a 30-foot deep acting area, it's going to be hard to keep the arrival time between 5 and 30 milliseconds, isn't it? Okay, so usually you can really only make this work for a 20-foot acting area. And if they have to have a bigger acting area than that, then this gets a lot more complicated, because then you have to be changing input delays on the fly.
And so do you want us to be assumed, like, pick a 20-foot area
Yep.
and sort of assume that?
Yep, pick a 20-foot area and assume just, what I usually do is I figure out what's the farthest downstage they're ever likely to go, because they will spend most of their time down there, right? I mean, you know, when they're singing a song, they're usually choreographed downstage center. So assume that they will spend a lot of time down there and figure out where that spot is, and then just find a spot that's 20 feet or so upstage of that and say, all right, that's my area.
Do you also want us to like go on the ramp, onto the side as well?
Don't worry about that for now.
So you don't.
Don't worry
Because there
about
was
it.
like a pretty significant amount.
Yeah, don't worry about the set for now.
Okay.
This is your first time. I don't want to like introduce too many variables here. So
That's kind of
yeah, but you'll worry about that later. For now, just see if you can make it work for a 20-foot acting area downstage in the thrust with loudspeakers in these locations. Yes.
Will you please post this video?
Yes. So I'm really ultimately looking for two numbers from you. I want to know how much delay do I put on the front fill, and how much delay do I put on the center Q7. So that's all I need, two numbers. And of course you need to back that up, show me why that number is right. Okay. So on Monday we'll go through them. We'll see how each of you did. I just made that look probably easier than it really is. Just heads up. This is the concept is simple, but it's a lot of variables to keep track of at one time. The math is not hard. It's all just 2 plus 2. But it's a lot to keep track of. That's why I use the Excel to do some of the math for me, is just to keep track of all of that stuff. Okay, but the good news for you is you don't have a balcony, right? So this will be easier. All you have to do is make it work for the front row and the back row. So that's better. And yeah, you should be good. Any questions? So give this a shot. I'm not expecting to be blown away by what you deliver on this thing. This is hard. There are actually not a lot of people out there that are really good at doing this. Okay, this is really hard to figure out. So, I won't be surprised if some of you come back on Monday with something that's kind of a mess, because it's your first try. Okay, I just want to see you give it a shot. Okay, give it your best shot, and we'll pick it apart and figure out where you went wrong, and we'll fix it. Okay. But if you can figure this out, if you can get good at doing this, this is. There are a lot of companies that hire me to design their musicals because they want that kind of a sound. They want that natural sound. They don't want it to sound like the sound's coming from the ceiling. They want it to sound like it's coming from the person. And I've gotten really good at figuring that out. And so if you can get good at this, that is a skill that people will pay you specifically to accomplish for them.
This plus that was.
Yeah, I mean, so yeah, you have to now take this and put it into the mix of all the other things I've told you to care about this entire semester. So you also have to care about loudspeaker coverage. How do you get the sound to go where you want and not where you don't want it to go? You have to worry about that. You got to worry about gain before feedback. And now you got to worry about time. And frequency response, because you don't want it to get obliterated by cone filtering. And you have to worry about sensitivity, that is the loudspeaker actually able to get that loud. These are, you have to worry about all these things all at the same time. But that's not till the end of the semester, right? So that's what we'll do for the final project, is I'm going to give you a project where I'm going to say, okay, now you have to care about all these things all at the same time, as opposed to only caring about them one at a time, which is
So
what
we're not caring about that kind of speaker.
don't care about that right now. It doesn't matter that it's a Q7 or an E3. It's just a loudspeaker. Assume that it's right. Assume that it's in a good place and that it covers well and that you'll get good gain before feedback and all that stuff. And then later, you can worry about that stuff after you've looked at just time all by itself. Okay? Any other questions? All right.